So last week we talked about non-ideal vapor-liquid equilibrium, and all of that ideality that we focused our attention on was in the liquid phase. So to start this week off, and I believe this might be our last phase equilibrium lecture before we move on to chemical equilibrium, which is going to be our last continuum scale content, and then we're going to move on to statistical mechanics. So in stat mech, just as a quick preview, thermodynamics has been developed over the course of probably the last 500 years. In sincerity, maybe over the last 200 years with the Industrial Revolution, where we really had a clear, well, not a clear, a concept of entropy, for example. Stat mech, statistical mechanics, is the application of effectively Boltzmann's atomic theory to thermodynamics. So what Boltzmann was able to do in the late 1700s, he was able to demonstrate that if you treated fluids as the random movement, basically, of lots of little particles, that you could really accurately predict fluid properties. No one really believed him, but as it turns out he was right. So atomic theory, and what we kind of now know as the structure of the atom, sort of came into existence in the late 1800s and early 1900s. You know, quantum mechanics came about sort of in the 1920s. So what statistical mechanics is a relatively new field, about 120 years old, that in order for it to sort of gain traction, it had to predict the same things that classical thermodynamics did. So statistical mechanics is basically redoing everything that we've done in class, but from the perspective that all of matter is made up of atoms and molecules. So if everything that we've done right now, we can base all of our classical thermo on basically, let me think about this, 2 to 3 properties. What is the heat capacity, and what is its relationship between pressure, temperature, and volume? So with an equation of state and heat capacity, we can basically do everything in classical thermodynamics. That doesn't require us to know why certain molecules have a certain heat capacity, for example, or why certain molecules behave differently on a PV isotherm. Stat mech is what allows us to say, here is the molecular structure, here's how those properties predict heat capacity, here how those properties predict the PV isotherm. All right, that's what we're going to be moving on next. Now that's obviously a large field of study, so some universities at the graduate level, they don't even have classical thermo. They just assume that everyone's an expert and they only do statistical. But I think it's nice to have sort of a balance. So we are in the closing days of classical thermo, about this week's worth of content, and then after that, we're going to go into the molecular and statistical world. So today, we will talk about liquid-liquid equilibrium, but a lot of the stuff that we'll be talking about is actually sort of general phase equilibrium. We're going to be using liquid-liquid equilibrium as sort of a vessel to talk about it, but a lot of the concepts that we'll be discussing are going to be appropriate for any of them. So in liquid-liquid equilibrium, all the same concepts that we have talked about still apply. Right? All of our formulations of fugacity and partial fugacity and equilibrium criteria, it doesn't matter what the two phases are. So we still have thermal equilibrium, where all of the temperatures are constant across all of the phases. We have mechanical equilibrium, where all of the pressures are constant across all of the phases. And we have chemical equilibrium, which is the one that we are interested in. Now we can write this sort of generally, that the chemical potential of species I in phase 1 has to be equal to the chemical potential of species I in phase 2, so on and so forth. But in constant temperature pressure systems, which is what we typically are going to care about, this relates to the partial Gibbs. And you're going to have one of these relationships for every single component in your system. Now, if you read thermodynamics literature, they will almost always use the notation of the chemical potential. But what I find for education purposes is it's a little bit easier to do it explicitly for the partial Gibbs. Now the chemical potential is more broad because, and oftentimes for liquid-liquid systems specifically, we're not going to be working in the NPT ensemble, right? We'll be working in the constant volume, constant temperature. The reason behind that is because the changes in density are going to be somewhat insignificant. And so from a strictly mathematical perspective, it's easier to do the math for a constant volume system. So that's why a lot of times you'll see the chemical potential written in the nomenclature, and for a liquid-liquid system, we'll be assuming an NVT, so a constant volume system. But it's just easier because it continues on with the phase equilibrium that we've been doing for vapor-liquid if we just stick with the sort of constant pressure, constant temperature systems. It's a little bit easier. But just note, if you ever do look in the literature for liquid-liquid equilibrium, it's almost always constant volume. So, again, we don't have to do anything differently. All the equations that we've derived so far are completely generalizable. So what we've done instead of using the partial Gibbs, we have instead used the partial fugacities. And we've talked about this a little bit, I'll highlight it again. That's because there's a discontinuity in the chemical potential in dilute systems. So using the fugacity lumps all of that discontinuity into a factor that we get rid of. And that's what the ideal gas mixing is. So for a liquid, the partial fugacity of the liquid, we model it here as the mole fraction times by the activity coefficient multiplied by the pure species fugacity. Now this is in the equation sheet, right? So if you go back to your equation sheet, you'll see there's a section that was invisible probably on the first exam for all of you that highlights all of the multi-component phase equilibrium expressions that we're going over. So for liquid-liquid equilibrium, we have the fugacity for species I in phase 1 is equal to the mole fraction in phase 1, the activity coefficient in phase 1, the temperature and pressure are constant, so I don't have to add any superscripts, but the composition is dependent only on the composition of phase 1 for the activity coefficient of phase 1. And then this is equal to, oh sorry, missing something here, multiplied by the fugacity of the pure liquid at constant temperature and pressure. Now I set this equal to the partial fugacity of the same species but in phase 2. The only challenge of liquid-liquid equilibrium is a battle with nomenclature. So in this case here, we have the mole fraction of species I, but in this case in phase 2. It's going to have a new composition of the second phase, which is going to require a new activity coefficient. In this case, the activity coefficient depends on temperature, pressure, and the composition of phase 2. But it also depends on the pure species fugacity. So when I set these two expressions equal to one another, I actually don't really need all that much information about the pure fluid because those both cancel out. So in the case of two-component liquid-liquid equilibrium, I'll call this 1 and 2, we have two expressions that we have available for equations to help us solve our phase equilibrium. We have the mole fraction of species 1 in phase 1 multiplied by the mole fraction of species 1, sorry, the activity coefficient. I'll leave out the dependencies here just for a second. Equals the mole fraction of species 1 in phase 2, the activity coefficient of species 1 in phase 2, and the mole fraction of species 2 in phase 1, activity coefficient of species 2 in phase 1, mole fraction of species 2 in phase 2, and activity coefficient of species 2 in phase 2. If you're not careful, superscripts and subscripts can be very easily confused in liquid-liquid equilibrium. So what we have here is, let's say, assumably, we have a model for activity coefficient. And for an example, we will use the one constant Margulis. So if we have an activity coefficient model that's tuned, we can calculate all 4 of our activity coefficients. So then what we're left with is 1, 2, 3, 4 unknowns. So we need 2 additional equations. Which 2 equations are those?
Temperature and pressure.
So temperature and pressure being constant, we're going to assume that right from the start. So we have the activity coefficient model. So if we have an activity coefficient model, what are the 2 missing equations here? This is very similar to vapor liquid.
The equation of the mole fraction.
Exactly. So the last 2 equations are that. The mole fraction of species 1 in phase 1 plus the mole fraction of species 2 in phase 1 is equal to 1. That's a definition. This is a mass consistency relationship. And then lastly, mole fraction of species 1 in phase 2 plus the mole fraction of species 2 in phase 2 is equal to 1. I hope it's starting to be clear what I mean. It's a battle of nomenclature with liquid systems. Because since they're both liquid, it's hard for you to say which is one versus the other. So the convention oftentimes is that if it's a 1-2 system, if they look, AB is probably easier. So if you have an AB mixture, you'll typically say one of the 2 phases is A rich, the other one is B rich. So if you have an oil-water system, you're going to have the oil-rich phase and you're going to have the water-rich phase. So if you can come up with a better nomenclature, then for sure adopt that. But as a generality, we write phase 1 and phase 2. All right, so for the one constant, Margulis expression, what we do is we modeled the excess Gibbs as a polynomial. Really simple. The result was that the partial excess Gibbs, for let's say in this case, material 1, is equal to just a coefficient, and it is related to the composition of species 2 squared. Now, by the definition of the activity coefficient, this relates it to the activity coefficient. So all the activity coefficient is a scaled form of the excess Gibbs. Now, if we look at this functional form right here, the reason why it kind of makes sense like this is that as you get to a pure material, your activity coefficient should go to 1, your excess Gibbs should go to 0. So in this case here, as the mole fraction of species 2 goes to 0, that means that the excess Gibbs of species 1 goes to 0. As the mole fraction of species 2 goes to 1, that means your excess Gibbs goes to some finite value. That's your activity coefficient at infinite dilution. Right? That's the most unhappy that you would expect your fluid to be. Right? When it's surrounded by a sea of all of its enemies. Okay, so we rearrange this expression. So that means the activity coefficient of species 1 right, just a simple algebraic substitution. What I've done here is I've just substituted 1 minus x2, sorry, 1 minus x1 for x2. And then we just have to put it all together. And we will get our 2 equations and 2 unknowns. So mind you, this is the simplest form of liquid-liquid equilibrium that we can write. So bear with me. We have the mole fraction of species 1 in phase 1 times by its activity coefficient model. Right? So this is the expression for the partial fugacities of phase, component 1 we can write the same expression for the partial fugacity of species 2, but I'm going to make a substitution so I can get this down to 2 equations and 2 unknowns. You'll notice here that the 2 unknowns in this particular equation are the composition of species 1 in phase 1 and the composition of species 2 in phase 2. Sorry, composition of species 1 in phase 2. So I'm going to use these 2 unknowns to write my next liquid-liquid equilibrium expression. So in this case, it'll be 1 minus noting that this here is just x2. And that's it. That's liquid-liquid equilibrium. Now, the challenge is that this is the simplest of activity coefficient models. Real activity coefficient models will be a little bit more involved, but in general, if you're solving this numerically, you don't have to actually write out these explicit expressions. You can do it in the computer and let the computer do the algebra, which I would highly recommend. If you don't have to, do not do this by hand. And then obviously for an exam, am I going to ask you this on an exam? I don't expect that everyone has the ability to solve a system of nonlinear equations on their calculator. So instead we'll do graphical stuff. So let's talk about that. First of all, any questions on liquid-liquid equilibrium? The concept of theory, identical to vapor-liquid. The only difference is how we model our partial fugacities. In this case, it's an identical functional form, so it simplifies to a little bit different one. But other than that, vapor-liquid equilibrium, Raoult's law is just particular applications for substitutions of the partial fugacity. In the future, if you ever find yourself encountering solid liquid equilibrium, it's exactly the same. Just substitute in what the best approximation is for the partial fugacity of the solid, and you're done. So, because liquid-liquid systems are so non-ideal, it's a useful exercise to take a look at how the Gibbs free energy changes across the whole composition, because it teaches us quite a lot. So, the Gibbs free energy of an ideal mixture, right, and we can think of this as a function of temperature, pressure, and composition as well, right? We're going to be varying the composition to look at the graphical effects. We'll assume the temperature and pressure are constant. It makes our lives a lot easier. We're going to be mixing them in a constant temperature pressure situation. Okay. Intensive and extensive properties. You guys remember those? Okay. Enthalpy is intensive or extensive? Extensive. Entropy is intensive or extensive? Extensive. The more material, the more enthalpy, the more entropy. So that means when I look at the Gibbs free energy of the mixture, I have to consider the Gibbs free energy that is coming in from the pure species. They're going to have their own enthalpy, they're going to have their own entropy. Which means that even in an ideal mixture, I'm going to have a weighted average of the Gibbs that is coming into the system from those species, because it's extensive. They're contributing to the mixture. Now for enthalpy, it basically stops here, if we're assuming it's ideal, right? Because the excess Gibbs is the delta H of mixing. If there's no delta H of mixing, there's no excess enthalpy. But in the case of entropy, even in an ideal gas mixture, entropy is being generated by the process of mixing. Two fluids are never going to spontaneously unmix. So even in an ideal mixture, we have an additional contribution here from the entropy. Right? This is just based on the extensive nature of enthalpy and entropy, and this is based on the ideal gas entropy of mixing. Now this term is always going to be negative, right? Because the natural log of a number that's less than 1 is always negative. So if we look at the Gibbs of a real mixture now, we're going to have a contribution from, actually let me do one more quick substitution before I jump into this one. Try to redefine one other term. The Gibbs free energy of mixing then is just going to be like so. Right, this is the pure species, this is the total. The difference between those is the delta G of mixing. So now the total Gibbs of the system as a function of temperature, pressure, and composition is going to be equal to the contribution of the Gibbs of the pure species plus the entropy generated from mixing and the total excess Gibbs, which is going to be the contribution to non-ideality. So I'm going to go over here and start to graph this out. So effectively what I'm going to be plotting is the total Gibbs of the system so that we can visualize under what circumstances can we minimize it. If the Gibbs is minimized only once, that means the whole system is in equilibrium as a single phase. If you have multiple minimas, that means that the global minima is going to be by partitioning that into two separate phases. So what I'm going to look at here I'm going to write this as, I'm going to use A or B, I use 1. Okay. So this is the mole fraction of component 1 in the total mixture, which means that some arbitrary position up here is going to be the Gibbs of pure species 1. And down here, this would be the Gibbs of pure species 2. Now, oftentimes when we're going to be doing this in the future and in homework, you can set these as reference conditions to be 0, so that they're at a level position. It makes the analysis a bit easier, but for this purpose, we're going to make it a little bit more complicated. So the first contribution here is really going to be just the weighted averaging between those two. So this is going to be the total Gibbs, and in fact, I need to read, let me see, no, I'll keep it here. I'll just go negative. That'll make this work out. So the first is just we can have a, that's how much Gibbs is going to be contributed to the pure systems unmixed. Now in the case of the one constant Margulis expression here, where we're going to be modeling G1 excess. We'll be modeling our excess Gibbs from the one constant Margulis expression. What that means is that when A is equal to 0, that means we have no excess Gibbs, which means we have an ideal mixture, and the graph will end up looking something like this. This is going to be for A equals 0. Now we'll see that no matter what composition we construct, the Gibbs is always going to be lower of the mixed system than of the individual contributions of the Gibbs free energy to start off with. And in fact, this slope right here is minus infinity. And this is something we've talked about a little bit, and this is the whole reason why we have to define fugacity in the first place. So the Gibbs drops at a rate of minus infinity when you start to mix two processes together. So effectively, there is never going to be an activity coefficient model that has an infinite slope at the low dilution in order to counteract that. So that means that no matter what happens, no matter how much the two fluids hate each other, you will always have a local, teeny little dip in the Gibbs free energy at really dilute systems. So everything is always miscible in everything else, to at least a very trace amount. It could be a very low quantity, but you will always have miscibility. Now, so as we increase our excess Gibbs, in this case for this model, that's by increasing A. So in this case, let's say this is A over RT. Now, if we increase it a little bit, let's say this is A is equal to 1, we'll increase it a little bit more. This will be A is equal to 2. And eventually, around A equals 3, we'll have some new behavior occurring. Now, I've drawn an exaggerated version here. A being equal to 3, it crosses over the summation of the weighted average of the Gibbs. You can still have a system where the Gibbs is below this line and you still have phase separation. Right? The key thing is what is the global minimum, not necessarily what is it less than. The contributions. So, let me get a different colored marker here so we can talk about this. When we look at this plot here, it's not obvious here. We may want to think that the fluid will phase separate into these two Gibbs energy wells. It's easier to see when it's sort of flattened out, but the actuality is that if you draw a tangent line from here, oh my gosh, let's see if I can get it. Yeah, it's kind of curved, to there. Two tangent line connections. This will then give us the composition of X1, and we'll call it arbitrarily phase 1, and this one here will correspond to X1 in phase 2. This will be the minimum Gibbs free energy of the mixed system. Equilibrium in a constant temperature pressure system is obtained with minimum Gibbs. Additionally, we can draw two other boundaries to this graph. One we call the binodal. The binodal is the series of points that constitute the phase diagram. So in your TXY diagram, your binodal lines are your dew and your bubble curve. Right? This is a nomenclature, again, that you don't see very often until you crack open the thermodynamics literature, and it's like they're speaking a whole different language. Now, stability. What is the stability criteria of the universe that we based most of our derivations on? Has to do with entropy. Greater than or less than 0? Less than 0. Right? Entropy always has to be concave, which means that Gibbs always has to be convex. Meaning that this region over here, you have a stable fluid. And at the inflection point, we can draw an additional boundary. This region here is called the spinodal. So in this case here, we have stable fluid. This is unstable. And again, we have a stable fluid. So, let's be pure component 2 and march ourselves down as we slowly titrate a little bit of component 1 into the system. So if I find myself at this point right here, at this composition, at this temperature and pressure, how many phases do I have? 1. Here, same. Here, same. Now if I add a little bit more of component 1, do I necessarily infinitely quickly phase separate? Right? This is exactly the same equivalent of something like a superheating or subcooling. And I'll show in a moment that it actually takes energy to phase separate, so it doesn't happen instantaneously. Thermodynamics is the infinite long-term solution. However, as soon as I cross this spinodal line, I will, as fast as diffusion allow me, begin to phase separate. And that follows a phase separation procedure called spinodal decomposition. Now in between this region here, where the curvature is positive, which means that our fluid is stable, it precipitates or phase separates through a process called nucleation and growth. We'll show videos of that in a moment. But if I'm anywhere before the first binodal, I'm a single phase system. Likewise, if I approach it from this direction over here, I'll be a single phase. As soon as I cross the binodal, the global Gibbs free energy minimum is going to be a tangent line connecting those two dips. Now what I'll do is I'm going to repeat this experiment as a function of temperature or pressure or whatever other parameters you want to do. So if I have temperature here and I have the composition of species 1, I'm going to plot the binodal and the spinodal position as a function of temperature. Now in the case of the one constant Margulies expression, right, as you increase the temperature, right, we're increasing the relative contribution of the excess Gibbs. So the two fluids are going to be more and more happy with one another. Not all fluids behave this way. So there will be some temperature above which we will have no two-phase region. This is called the upper consolate temperature. Upper consolate temperature. They also have, for a lot of fluids, a lower consolate temperature. So what it'll look like is I will have a binodal region. As I lower my temperature, the solubility of component 1 into component 2 will decrease. Likewise, component 1 into 2 will decrease. Right? The size of the two-phase region grows, meaning that the maximum solubility, in this case here, so this is x of 2 equals 1, this is x of 1 equals 1. So if I have pure component 2, the maximum solubility that I can dissolve component 1 is where I hit that binodal line. As I increase the temperature, I increase my solubility so I can add more of component 1 into component 2. Now I can also draw a second curve. This is the spinodal. Once I fall inside the spinodal, I have something that is an unstable fluid. It will not be able to exist at all. But I can supersaturate to within the region between the binodal and the spinodal. Once I hit that supersaturation limit, I will create an unstable fluid, and it'll decompose following a spinodal decomposition process. Now, a lot of fluids, polymeric systems, will also have something called a lower consolate temperature, meaning that as you heat two things up, you can actually get them to phase separate as well. So liquid-liquid systems don't have to behave at all intuitively for how you may think it would happen. So just to exaggerate things a little bit, this is a sort of a rare circumstance when thermodynamics informs kinetics. So if I have a region, I'm going to contrast two different regions here. In this case, the Gibbs free energy is going to be stable, so it is going to be greater than 0. In this case, the Gibbs free energy is going to be less than 0. It's going to be unstable. So here, we have some sort of a convex function. Here we have some sort of a concave function. Now the definition mathematically of how we determine whether or not a function is convex or concave, let's see if I can, don't want to botch my mathematics here. So if I have some perturbation, so if I start at some position here, now it's easiest if I were to start right there, and I call this my reference condition. And I perturb this system by splitting it into two, a region with slightly different Gibbs free energies. And this could be, for example, x1. So I will split it here into delta G2 and delta G1. Now a system here, so a system that is, in this case, convex, follows this behavior here, meaning that the energy, or the Gibbs free energy of the split system is always going to be greater than the Gibbs free energy of the initial system. Now, of course, if I were to put the starting point here, it's really easy to see, right? Because increasing it going either way. But it is true for all convex functions, regardless of where you fall on a convex curve, this holds true, right? So it doesn't have to be the exaggerated form. So in this case here, the Gibbs increases if you're trying to phase separate. Does that make sense to everyone? So if this is my mixture, I instantaneously mash these two components together. They're going to want to try and phase separate if that's truly the global Gibbs free energy minimum, which means they're going to split into two little microphases of slightly different composition. Right? This is the early stages of these molecules trying to diffuse around. Now they'll find that those two phases have a combined total greater Gibbs free energy than the original one. This is exactly the same as the definition of a convex function mathematically. Now the opposite holds true in a concave function. On a concave function, if I split the split function will have a lower energy than the total one. So in this case, the Gibbs free energy always goes down. Now the consequence for this is that the molecules effectively feel that no matter what they do, they're like striking it rich. Right? They're in Vegas, and every time they roll the dice, it's perfect. That's what's happening in an unstable concave system. Which means that every molecular rotation, every molecular vibration, every slight movement and change of the molecule will lower the free energy of the system. Which basically means that kinetically, the fluid will, as fast as diffusion will allow, will phase separate. Right? Because molecules are still dumb. They don't know what's going on. They only bounce around by random walk. So in an unstable fluid that's concave, they will always, no matter what they do, will find a way to lower the free energy of the system. In a convex system, they have to be a bit more coherent because every movement that they change and every movement that they do actually raises the free energy of the system. Right? So they have to find a pathway such that you can phase separate. Basically, the size of these fluctuations get larger and larger and larger until they can find a way that they can form a large nucleation droplet. So, what I'm going to do is see if I can hook my computer up, and I will show you some videos or simulations to highlight the difference between nucleation and spinodal decomposition. Bruno, does anyone have any questions about the mechanism that we talked about here? There we are. So this first one here is a very exciting video of water boiling in slow motion. Pull the screen down. So when you boil water, it's going to be a stable phase transition. And so you can see what happens is that you get little bubbles that form on the bottom. Now early on in that stage, the bubble forms and disappears, forms and disappears. Only until the bubble reaches a certain size does it become stable enough to grow. And that's due to effectively how strong the surface tension is, right? That tells us here that when they form an air interface that has a higher Gibbs free energy due to the increased contact area between the vapor and the liquid. So a nucleation phase transition is going to be similar to if salt is precipitating out from a supersaturated solution as well. Boiling water is exactly the same circumstance. So oftentimes when you're boiling water, it's imperfections in the, I'll turn autoplay off, otherwise YouTube will be taking us for a ride. Little imperfections in the cookware are going to be the reason why you get these nucleation bubbles to form. So, in the case of chemistry, this is why you add boiling chips to your chemistry glassware. Because if you don't have boiling chips and you're trying to heat something up, let's say you want to do your reaction with boiling temperature water, if it heated up, you'll be able to superheat it, and so as soon as you add your reagents, it'll shoot the water out like a cannon and scald you, right? So having really, really clean glassware with no nucleation sites allows you to control the homogeneous chemistry. But if your glassware is crummy like this pot of boiling water right here, all your chemistry is going to be occurring at the nucleation sites on the surface of your glassware, which kind of defeats the whole purpose of being a good chemist. Hence why I was never a good chemist. So to contrast that, this is CO2 going past the critical point. Now going past the critical point is a different type of transition. There actually is no phase transition when you meet the critical point. You have two phases, in this case, a dense CO2 phase and a liquid CO2 phase. As you heat up to the critical point, you'll notice that effectively all that's happening here is that this is getting less dark. The liquid is becoming less and less dense. The vapor is becoming more and more dense as you reach the critical point. And so once you hit it, nothing really boils. It just kind of disappears. So that's a big distinction between sort of a critical point and a phase transition. Just something I like to include. Now the next one here, before we get to spinodal decomposition, is just sort of a fun one. This is going to the triple point of tert-butyl alcohol. So I think I have it written down here somewhere. So critical point of CO2 is 31 degrees C and 73 atmospheres, meaning that it's something you can do in the in a classroom demonstration. You just need a high pressure source of CO2. Tert-butyl alcohol, its triple point is at 318 Kelvin, so about 45 degrees C, and 0.06 atmosphere. So all you have to do is heat it up on a hot plate and pull a vacuum on it. So it's another thing you can do in a classroom demonstration. So what they're doing right now is they're just pulling a vacuum. So it's actually going to be boiling. The fluid, eventually it'll kind of reach its saturation point where the vacuum pump is sort of tapped out. And then if you heat it up, eventually you'll start to see some freezing occur. So now we have liquid solid equilibrium, and it's boiling at the same time as well. So this is the triple point of the fluid. But it's a delicate balance. You got to make sure you maintain all the temperature and pressure conditions. So it's kind of neat though. But you can see all three phases of matter at exactly the same time. But due to degrees of freedom, there's no sensitivity control. It has to be at exactly the right temperature at exactly the right phase. Otherwise, it'll all freeze, all boil, or all turn liquid. Now, the last one here is spinodal decomposition. Now, this is a simulation because it's not trivial to see in reality, because this is a liquid system at a molecular length scale. So how one would visualize spinodal decomposition is through X-ray or neutron scattering, and that's not really a visual medium. So red and blue are two different materials, and this starting off is an initially random configuration, right? A random distribution of the fluid. Imagine this is a homogeneous, well-mixed fluid. Now what's happening is I've sort of covered up a little bit, but in spinodal decomposition, when you're trying to create a mixture that behaves this way, we'll start off at an elevated temperature system that's homogeneous. Now, if we drop the temperature into the binodal, that will mean that we should phase separate following a nucleation and growth mechanism, just like boiling water, right? We would form a bubble here of, let's say, phase blue, and then it would slowly grow. Now, alternatively, if we drop the temperature into the unstable region, meaning that the Gibbs free energy has a convex shape like this, concave shape like this, what will happen is that every single random movement of every single one of these particles, and in fact, this isn't a particle, we're modeling the spatial composition of the system, right? This is following a Cahn-Hilliard approach. This is the Cahn-Hilliard solution here, which is a fancy equation that models phase transitions. So what will happen then is that every single fluctuation in composition of the fluid will result in a system with lower Gibbs free energy. So what will happen then is you'll form effectively striations very rapidly where the concentration just gets enriched. There we go. So very, very quickly, when the boundaries are small, they can really quickly separate into the red-rich and blue-rich regions of the two phases. Now, as it goes on, you'll see this blue circle here. It's slowly diffusing basically through the red. You can find other regions here, right? The blue will diffuse out of the red and into the blue, and these small pockets will start to disappear. And depending on how you control this process, you can quench this even further to kind of crystallize and gel this or make a glass out of it, right? So this is a sort of an interesting step that can be used for the synthesis of polymeric materials, where you obviously have a really high surface area of contact between the two. So if you want to make some sort of a capacitor or something where you have a transition between those two phases, this is a trick that could be used, but it's also a phase transition mechanism, so spinodal decomposition. And slowly, the bigger pockets disappear like this, and eventually will go away. And then the final solution is going to be all red, all blue, right? It's going to be two big regions, but it takes a while for them to kind of get that across. So that one goes away there. This one's slowly getting smaller. Who knows how long I ran the simulation for? But I believe this is the solution to, like I said, the Cahn-Hilliard equation. This is a numerical simulation. So you'd have to start off with a random orientation of the system. All right, so that covers our non-reactive phase equilibrium. So spinodal decomposition also happens when you superheat and subcool, right? So there's a limit to how much you can superheat or subcool a system. Once you reach that instability point, the vapor and liquid will also phase transition following a spinodal mechanism. But the problem with a vapor-liquid transition like this is the vapor is very, very low density, the liquid is high density, which means it basically explodes. Okay. In the liquid-liquid system, the density of the two fluids doesn't change very much, and so it forms nice, pretty patterns like this. Let's see.
Yeah, so some of these you can see here how they're all becoming spherical in shape to reduce surface tension, and they're getting smaller because the blue is diffusing through the red to get back to the blue, but the rate at which it ripens, it's called Ostwald ripening, is dependent on what is the trace solubility of the blue into red and red into blue. Right? If red and blue were pretty miscible with one another, then this process would happen a lot more quickly. If they're very, very immiscible with one another, then it takes a long time for these becoming spherical regions, the individual molecules are diffused through the red, get to the blue. Any questions? All right, please come prepared with more questions on the homework for Wednesday, and have a good rest of the week. See you.